Welcome once again to this course on tectonics and geodynamics. We are now on to lecture number 5, dealing with rigid plates on the Earth's surface. Now, up to now, what we have discussed so far in the previous lectures was first of all to do with the evidence in favor of continental drift. So, the continents and the oceans exist on the surface of the Earth, and the continents, then the continents begin to, there is evidence that the continents were together, moved apart, they changed their latitudinal positions on the Earth's surface. So, there was a lot of geological evidence in favor of continental drift. But if you remember, the theory fell into disfavor because adequate mechanisms that could explain the physics of why or how continents could move could not be thought of at that time. At that time, the basic idea of continental drift was that the continents were cyclic and these were dynamic bodies that were moving on top of a static ocean floor, which was considered to be mostly silicon and magnesium, right. That is, it was called the CIMA. So, for a long time the sea floor was assumed to be static itself. However, after the Second World War, it began to be realized that the sea floor itself had topography. It was not just completely flat, there were mountain chains inside the ocean floor, there were deep valleys that we now call trenches inside the ocean floor as well. So, this means then that we had enough evidence on our side to actually say that the sea floor itself was a very dynamic entity. So, what did this, if we now combine the evidence of continental drift, right, with what we see for sea floor spreading, it was just a matter of time before people began to make this connection between the two. And this slowly led into the concept that forms the subject of today's lecture, that is rigid plates on the Earth's surface. Essentially then, what we are going to do in this lecture is to combine oceans, continents and the concept of rigid plates, all of these on planet Earth. Now, I stress this particularly because planet Earth itself, right, is one of the rare places that we know of where plate tectonics in the form that we see today is operating. Most of the inner planets, we have no evidence that plate tectonics has or is occurring at present on their surfaces. Whether they did occur, it did occur as a process in the past is not completely sure, but it is thought of that there are possibilities that plate tectonics could have operated in the past, but we do not know. What we can do is to best understand how plate tectonics operates on the surface of the Earth, and we will see that these are ultimately related to why the oceans and the continents are the way they are today on planet Earth. Now, let us just go back to what we were talking about and how ideas had evolved. So, if you remember this famous person here, right, this was Harry Hess. Harry Hess himself, right, he had proposed, he was the first to actually think of the sea floor as a very dynamic entity. Now, the sea floor itself, in his opinion, right, was something that was created at the mid-oceanic ridges. So, in the middle of the Atlantic Ocean, he observed that there were ridges, and in those ridges, right, there was a rift valley. This was all, this has been identified by Murray Tharp and Bruce Heezen before. He actually connected this, and he thought that this tensional stresses which are operating in this particular region, the tension operating here, right, meant that the sea floor was being pulled apart. So, material from the mantle was coming in, solidifying right at the ocean bottom here, formed a ridge here, then this material would be split apart and the ocean floor would move this way and this way away from the mid-oceanic ridges. Now, this would seem to imply that the sea floor, right, is expanding, which means overall the surface area of the Earth itself should be increasing with time. However, he also said that this was all probably an outcome of convection going on in the Earth's underlying mantle, and at that time he thought more in terms of the crust. So, the crust was actually, he said, being consumed at these deepest parts of the ocean floor, which we call trenches. So, this is a place, right, where you had compression going on. So, stress wise you had tension at the mid-oceanic ridges and you had compression occurring at the trenches, and the crust was being consumed at the trenches here itself. Now, all of these Hess speculated was a part of a convection cell in which hot mantle was rising, right, and cold mantle was sinking down. So, this was a part of the cold mantle sinking down, this was a part of the hot mantle which was rising. So, wherever the hot mantle was rising, you get a ridge, right, wherever the cold mantle is sinking is where you form a trench. On the surface, these are the visible expressions of the underlying convection that goes on in the mantle. And as we will see that this is largely or broadly correct even as we think today. Now, in all, what Harry was talking about, right, was that the seafloor was a dynamic entity. That was the crucial point. The seafloor, which was assumed to be static in the continental drift theory, was actually a very dynamic part, right, of the whole mechanism. So now let's just try to get back to where we think we were at the beginning of the 1960s. So in the 50s, if you remember, Marie Tharp's papers started coming out in the early 50s with Bruce Heezen, in which she identified the mid-oceanic ridges. The trenches had already been identified. So people began making these connections, and then Harry Hess, with his idea of seafloor spreading, brought about this idea that the seafloor was dynamic. However, even then, even by the end of the 1950s, in spite of all the evidence, there were two schools of thought governing broadly, driven by the position of the continents. So one concept was that the continents actually remained in fixed positions. Wherever they are today, the distribution that we see today is where they were in the past. The other school, of course, thought that the continents were moving on the surface. Now, the rigid Earth, as we call it, assumed that the whole surface of the Earth was rigid, so the continents were present in the past where they are today as well. And this was really supported by two models of the Earth that had been existing for quite some time. One model was called the contracting Earth hypothesis, the other one was called the expanding Earth hypothesis. Now, both of these ideas, these hypotheses, you can say, actually had very famous proponents. So, for example, the contracting Earth hypothesis was as old as Isaac Newton. Lord Kelvin, right, also one of the people who was fundamental in the idea of heat and how heat moved, he was one of the proponents of this, advocates of this theory as well. And you had a famous seismologist, Harold Jeffreys, who continued to believe this even till the end of the 1950s. So Harold Jeffreys, even till the end of the 1950s, supposed that the contracting Earth hypothesis really held good on Earth. On the other hand, there were other people who thought of the expanding Earth hypotheses, right, and this also included famous names. Paul Dirac, a famous physicist, right, Carey, as well as Runcorn, all of them, right, they believed that the Earth was expanding. And much of their evidence actually was based on these, the tensional features that you see at mid-oceanic ridges. Now, we will come to this a little while later. The opposing theory was that of the mobile Earth, and we will talk about this just after we discuss this bit about the rigid Earth. Now, the rigid Earth hypothesis, the rigid Earth model, really assumed that you had a crust. Now, this crust was fixed. So, if you had a continent, right, let us say this was a part of it was continental crust, and this was ocean, and let us say this is continent. The rigid Earth hypothesis assumed that this part was static, it was not actually moving, right. So, the lid that you say, we can talk about this as a lid model. So, this lid of the Earth, right, was in a static position, it was rigid. So, with respect to the interior of the Earth, there was no motion of the top. Now, the contracting Earth hypothesis, the whole idea, why was it so favored? The main reason is the occurrence of these mountain belts. So, mountain belts, especially say mountain belts like the Himalayas or the Alps, right, these were very prominently seen on the Earth's surface. People had done structures on them, documented the types of structures, the type of geometry which was built into them. And it was clear that if you do the geology of mountain belts, it was clear that the mountains had actually formed, right, because of compressional stresses. So, which meant that there was a lot of crustal shortening involved. So, the stress was compressional, and the stress was compressional, and the strain that resulted from this was shortening. So, you had some amount of shortening, crumpling of the Earth's surface, and that went very well with the contracting Earth idea. So, the idea is simple enough to understand. The Earth must have been very hot when it was formed. So, over time, obviously, it has been cooling, and as it is cooling, the Earth will contract. Any cooling substance is expected to contract. and that is what was happening to the earth as well, and that is why you got these crumplings, and that is why, and that is where you actually formed these mountain belts. So, this was really a model that was actually supported, right, by the contracting hypothesis, the contracting earth hypothesis. On the other hand, at the time when of Newton, at the time of Kelvin, right, by these two people were not aware, right, of any places on the earth that were actually extending. Now, that is places on earth which were in a state of tension. It was not known. There were brief ideas about the existence of rifts, right, but it was actually not very well known. The expanding earth hypothesis actually came into origin much later and came into origin in the 20th century itself, and largely after 1950, when it was understood that the mid-oceanic ridges were places where you had rifts of this sort. So, rifts are basically places where you get faults of this sort, and because you have faults of this sort, which are called normal faults. So, because you have these normal faults, it means that the surface of the earth, the crust of the earth is essentially accommodating extension. So, you are actually lengthening bits of the crust. Now, it was realized, and the seismic evidence that we got from the earthquakes at the mid-oceanic ridges also seemed to support what we were saying, that what scientists were thinking, that the mid-oceanic ridges were in a state of tension. So, the mid-oceanic ridges themselves, so if you think of it something like this, right. So, this was a part which was in a state of perennial tension. So, that meant then, and supported by the magnetic data, the geomagnetic data, what this meant, the rock magnetism actually supported the idea that the sea floor was actually extending. So, this seemed to support what we call the expanding earth hypothesis. Now, although they talked about an expanding earth and a contracting earth, right, when you are talking about a contracting earth, so the idea was the earth itself was actually becoming smaller, right. The expanding earth on the other hand was trying to think of the earth becoming, of the earth increasing. So, in that case then, you need not actually have large scale movements on the earth's surface. Just the fact that it is expanding meant simply that the crust of the earth is adjusting to the shrinkage or the expansion, as the case may be. This was the idea. You did not need to think of movement of the lid of the earth with respect to its interior, right. It was simply of the whole sphere of the earth either growing larger or smaller. So, all the accommodation was simply on account of that. Now, this was the basis of the rigid earth model. However, if we now go into the second part of it, the alternative idea, the idea of a mobile earth, right, this talked in terms, or this was thinking conceptually in terms of moving continents. And the biggest support for this, of course, was geology. I mean, it was the idea that the theory of continental drift. Wegener, of course, was one of the famous proponents of this theory. A geophysicist also, Runcorn, right, he actually looked at the results of rock magnetism, and in taking after the ideas of Dietz and later of Vine and Matthews and Morley, he knew that the results of rock magnetism seemed to indicate that the sea floor was indeed spreading, which meant this was consistent with an expansion of the earth. However, the mobile earth, that is a part where the earth is moving, was also, it was something that was implied through the idea of a convecting mantle, and the proponents of convection, large scale convection in the mantle, were actually by people who worked on experiments at high pressures, that is Griggs, with people who worked on the gravity model structure of the earth, Venning-Benez, and of course geologists like Arthur Holmes, who actually thought, right, that this would be applicable if the earth's crust or the upper part would actually be mobile, right, if we had convection. Now, this is probable because of some concept in physics which is governed by what is called the Rayleigh criterion. So, then if we now look at this mobile earth model, right, so what does this actually mean? One was, of course, the old idea, right, the earth had to be mobile, the continents were moving around, that is broadly the idea of continental drift. This was the idea that we have actually discussed in the first two lectures, so I will not repeat it. So, the ideas in favor of a moving lid of the earth, right, that was inherent to the theory of continental drift. But what about the other idea about convection in the Earth's mantle? Now, one of the things that you must understand is everything that's happening inside the Earth is really a question of energy. So, when the Earth was formed, when the solar system was formed, it really meant, right, the coalescence, the conversion of a large amount of gravitational energy into heat energy. Coupled with that was the presence of spontaneously radiogenically breaking elements right inside the Earth, disintegration inside the Earth. That was actually one of the common things that happened inside the Earth. That was also generating a lot of heat. And because of this, the interior of the Earth has to lose that heat. Now, when this happens, if there is a temperature difference between, say, a part here and a part out here inside the Earth, then heat will be transferred. If T2 is greater than T1 temperature wise, then heat transfer will take place from here to here. Whether that takes place by conduction or convection, right, depends upon something called the Rayleigh criterion. Now, we will talk about this in a little more detail later on in this course, but broadly here, what it means is that if you actually make the stuff hot enough, it will become less dense here, it will become lighter, less dense than the stuff here, which would then mean that this would actually experience an upthrust. It would tend to move up and the cold material would tend to go down. Now, whether or not material is able to go up or go down depends upon the viscosity largely of this material. There are other parameters, but the viscosity is a very big parameter here. And the viscosity was assumed to be, the viscosity of the mantle, it was assumed at those temperatures to be low enough to permit movement to happen. So, it was generally now accepted by the end of the 1960s that or by the end of the 1950s that probably there was some kind of heat transfer by convection going on. Now, if convection occurred, then cells, hot stuff would move up like this and move up to the side, and as it moved, obviously it might create tension out here. So, this was the idea that the lid might actually move because of underlying convection. So, the mobile Earth model was actually supported by continental drift, which was largely supported by geologists and some geophysicists, and there was the underlying physics concept of underlying convection inside the mantle, which might be responsible for actually driving what we consider to be continental drift, right, movement, horizontal movement on the Earth's surface. So, the dispute was essentially whether there was significant horizontal movement on the surface of the Earth. That was the problem. Was most of the movement largely vertical, or was there significant movement in a horizontal direction? That was really the crux of the problem. So, the idea is then, what we saw is that if you looked at those regions of the Earth where there were glaciers, so much of the Europe and North America where these theories were formulated, they had glaciers which during the last ice age. Now, as the glaciers were melting away or retreating, the load of the ice as it was removed resulted in a post-glacial recoil. That was a rebound. And on account of that, if it was rebounding, this was attributed to some kind of flow in the mantle. It had to be, otherwise there couldn't possibly be a rebound like that. Now, if the mantle could flow, that means the viscosity of the mantle, which you can calculate from that glacial rebound, this was actually a much lower value. And it meant that that critical Rayleigh number, according to the Rayleigh criterion, so if there is, according to the Rayleigh criterion, if you exceed that critical Rayleigh number, right, then the system will begin to convect. And indeed, for the mantle, it indicated that probably that number would be exceeded, and therefore the mantle would be expected to convect. So, what was then generally now agreed that convection cells occurred below the mid-oceanic ridges. These produce tension at the surface, and you would also produce a line of active volcanoes on the mid-oceanic ridge because of these rising currents. Similarly, these rising currents would actually sink right below the continental mountain belts, all below deep ocean trenches, and this is where the crust you'd maintain the surface area to be constant. But there was a problem. And the problem was, apart from the line of volcanoes in the mid-oceanic ridge, there are linear chains of volcanic islands. These are, for example, associated famously with the island of Hawaii, right, which did not lie on the mid-oceanic ridges. Now, these linear chains of mountains had peculiar properties. Now, we will just take a look at what these linear chains are. So, let us actually look at the Pacific Ocean. Now, the island of Hawaii is actually here, right in the middle of the Atlantic. So, this is where Hawaii is. And if you look at where Hawaii is, you'll see that there is a line of volcanoes stretching all the way back. So, this whole chain that you see here, so there is a chain of volcanoes, a line of volcanoes pretty similar to the ridge, but these are actually islands, some of them are submerged. So, the older islands are mostly submerged, the ones which, for example, Hawaii is still an island, so it is above mean sea level, but this is a linear line and it is by no means the only one. Now, if you look at these ridges themselves, they actually differ from the mid-oceanic ridges in several ways. Now, the characteristics of these Hawaiian volcanoes is, first of all, these island chains were all volcanic, they were absolutely straight, and you can see how straight they are, they are absolutely straight lines. Now, these chains, these are not located near the mid-oceanic ridges, they are not located near trenches or subduction zones either. So, here for example, this is the mid-oceanic ridge, these are the trenches, and you can see that these line of volcanoes is significantly distant from either the trenches or the mid-oceanic ridge. So, how do you actually explain these line of volcanoes? Now, each individual volcano, as you go on, if you move back, each of these volcanoes seems to be more and more eroded as you move northwestwards away from Hawaii, right. Also, if you look at the fossils, right, in these fossils tend to indicate that the volcanoes are older. So, you have a line of volcanoes, many of which are submerged. So, these volcanoes, as you move back, the further they are from Hawaii, they appear to be more and more eroded, and as you move back further, the fossils that you collect from the tops of these volcanoes indicate these volcanoes are progressively older as you move away. So, you could get something like 20 million years here, something like 50 million years here, and further back. So, you can actually see a progression in the ages. So, initially then, to explain this, people suggested that probably each chain was formed, there was a fracture along the ocean floor. So, there were faults or fractures, and that is where the magma was erupting, it was actually erupting along these fractures. However, people tried to detect these fractures geophysically, we can do it. There were already by the 60s, there were enough methods by which we could detect what was happening at the ocean floor. The fissures, these proved to be elusive, people could not find these fissures. And as you move to the southeast of Hawaii, right, if you expect there is a fault, you would expect it to continue southeasterly, but along that trend, nothing could be detected. So, if you went into this region, there is no extension, no detection of any kind of fault whatsoever. And finally, of course, there were earthquakes associated with this Hawaiian chain, but these earthquakes were not associated with any fault plane. They seem to be entirely explicable simply by the eruption of volcanoes. So, when a volcano erupts, obviously there will be some movement of the overlying ground, and all the earthquakes that occurred in Hawaii could be explained by these volcanic eruptions. So, it was a clear distinction between the Hawaiian type chains of volcanoes and the mid-oceanic ridges. The other thing, of course, if you look at the Earth's surface now, you will see that Hawaii is not the only one. This is in the Pacific Ocean. In fact, in the Pacific Ocean, you have another very important one as well. You have a submerged oceanic plateau called the Ontong Java Plateau, and you have this linear trend with a kink, right, also observed with ending in an active volcano here. Even with respect to our own country, India here, you can actually detect, this is a very rough depiction, that you can get a chain of volcanoes moving away from the Deccan Traps in India, and the active volcano center is in the Reunion Islands here. Similarly, you can move down here along a ridge called the 85 East Ridge, and it terminates in an island called the Kerguelen Islands, similarly the Mariana Islands. So, all of these are active volcanic centers, each of these are at the end of a line of volcanoes in which the volcanoes become progressively older as you move away along the line, along that particular chain, as you move away from the currently active center. Now, this is very, very interesting, because what you are seeing now, right, is not explicable in terms of what we see in the ridges. So, already then by the early 60s, there was sufficient evidence to say that the sea floor was spreading at the ridges, it was sinking at the trenches. And you can explain that in terms of this, that if you have a convection cell like this, then right above the convection cell, right, where the cell was coming up this way, you would get a volcano through which eruption would take place, and this would explain the position of the mid-oceanic ridge. Now, this is simply a rift valley which goes into the plain, as you can see here. If it goes into the plain, that means you would expect a line of active volcanoes right above this rising convection current. So, everywhere it rises, so along this line you would see active convection, you would see active volcanoes present. Now, When this chain is above the mid-oceanic ridge, the origin, because it's fixed, the ridge would be fixed with respect to the origin of it. So, whenever the rising current is, you will get a volcano on top. So, there would be a constant supply of heat and you would get constant volcanism. This was understandable, we could explain this. The problem, of course, was to explain the Hawaiian chain, because the older volcanoes, as you move away from the island of Hawaii, the older volcanoes were all extinct volcanoes. These are not currently active. So, as you move away, these would actually, being that these volcanoes were formed on a mobile sea floor, right, but these things are not active now. So, if there was a fault continuously all the way through, all the volcanoes should be active, and that is not what we see. So, in 1963, a Canadian geophysicist, J. Tuzo Wilson, who initially was actually against continental drift and the plate tectonic theory, or rather continental drift, he formulated plate tectonics. He suggested a mechanism by which volcanoes could form at a distance from the mid-oceanic ridges, right, or from the trenches. How could you get volcanoes, a line of volcanoes that could form away from it? And his idea then was that if you had to form volcanoes at a distance from plate boundaries, he suggested that if you have a surface layer of the earth, right, which is moving over a convecting mantle, that is, if you have, let us say, this is a layer, right, and the source actually lies here, sorry. So, if you have a layer and this actually lies, the source is lying below this part here, then in that case, then the source of the volcano is here. So, as the magma rises, you would get a volcano formed out here on the surface, but then if this is now moving, so if convection is happening this way, right, convection is happening this way and this part is simply being pulled apart, then you can actually form something out here, right, as a ridge which would be static at one position. However, if this is already moving and the source that you have here is at a distance away from the ridge part itself, then in that case you would get a volcano here which would then move away as this, because this plate is moving, right, or this lid is moving, as this lid moves away, the volcano here, right, would actually move to a position next to it and it would no longer be below its source, therefore, it would slowly become extinct. Now, this he presented in his famous paper in 1963, which was, incidentally, he could not publish this in any geological journal. So, he had to publish this in the Canadian Journal of Physics in 1963. And what he was suggesting was this, that above the ridge you had these volcanoes, but the source that you had, he actually thought that the inner part of the mantle was probably actually static and it is only a jet stream like thing which actually was creating the convection. So, he was saying that the surface layers of layer of the earth was moving, and because of that you would get an active volcano below the source at any one point. As the lid moved away, the active volcano would move away and become an extinct volcano. It would then slowly, it would get eroded by the ocean water, its top would be eroded, right. So, progressively as the lid began to move, the earlier volcanoes would simply move away from the volcanic source, right, and you would get a chain of islands, all of which would be volcanic in nature, they would be extinct. The oldest one would be the one furthest away, the one which is currently above the source would be the one which is active. So, he then suggested that you can get a line of extinct volcanoes on the surface this way. So, what he was implying is that the source must be below the layer that is actually moving. That was intrinsically the part that was important here. So, he suggested that within the mantle there must be hot spots inside the mantle that were hot enough to melt, and that must be below the seismic low velocity zone. Now, he assumed that the seismic low velocity zone was the part which was weak and the lid of the earth was the part that was above the seismic low velocity zone. So, if it is above the seismic low velocity zone, the lid would actually move, and as the lid was moving, right, you would get these volcanoes formed on top. So, you would get these volcanic chains like you see in Hawaii forming above this particular region. So, 1963, Tuzo Wilson, he proposed that a layer would extend from the surface of the earth to the seismic low velocity zone, right. He assumed that that was the lid, and this lid would move over the hot spots that lie below it inside the mantle, right, and you would form these volcanic chains. Subsequently, as his ideas began to evolve more, he then proposed a fundamental thing in 1965. He said that in that case, you can think of the entire surface of the earth being covered by rigid mobile plates, he called them. these plates were all sliding over the underlying seismic low velocity zone. So, all these plates were sliding over the underlying low velocity zones. So, he said then that the divergence, the plates were actually diverging along the mid-oceanic ridges, they were converging both along trenches as well as continental mountain belts, right. And also there would be places where the plates could actually move sideways with respect to each other. So, there would be a lot of different plates on the earth's surface, they would move sideways with respect to each other. Wherever they move sideways, you would also get earthquakes, but these boundaries would be different from those from the ridges, they would be different from the places where the consumption is taking place, that is the trenches. He called these sideways movement boundaries, he called them transform faults. So, these were different from what geologists described as transcurrent faults. Transcurrent faults were long faults on the earth's surface in which strike slip motion was taking place. Transform faults are also associated with strike slip motion, but they are different from transform faults. Fundamentally, they are plate boundaries, and there are other important differences which we will discuss later on in this course. So, essentially now, what was the schematic models of plates on the earth? So, you would have a mid-oceanic rift like this. The mid-oceanic rift can actually be displaced across these little units. So, the part from here to here would be a transform fault. So, this would be one of the boundaries along which plates are diverging, right. These would be parts along which plates would move this way, right. So, sideways. So, these parts would be transform boundaries, the part that's out here, these would be transform boundaries, right. After that, this is also ridge, and then there would be two types of consumption boundaries you can think of with respect to the oceans. One would be the ocean actually sinking below another ocean, below what's called an oceanic trench, but it's just as possible that the ocean can sink below a continent on the other side, right. There could be a trench here, right, and you can actually get a continent on this side. So, the plate boundary would be from here to here or from here to here, right, and this is also part of one boundary. So, it means then that all of this region was one plate, all of this region, right, would be another plate. So, this in fact would be a third plate, this one would have to be a fourth plate. So, you would actually get different plates like this on the surface of the earth. If you look at the surface of the earth today this way, you can actually demarcate plates on the surface of the earth, right, bound either by mid-oceanic ridges like these ones here, the red marks, by trenches which are all the blue marks here, right, and you can also have transform faults. Now, the transform faults are not marked particularly well, but there you can see these green or blue lines where there is some transform movement, that means sideways movements of plates along parts of these faults. So, this way you can divide the earth into several plates. And as you can see, for example, if you take either side of the Atlantic, a North American plate, you have a significant part of the North American plate which is both ocean as well as continent. So, this part of North America and this part of the Atlantic are actually part of one single plate. This part of South America and this part of the South Atlantic are also part of another plate. Similarly, this part and this part, the Atlantic Ocean here and the Africa and this part here are parts of the of what we call the African plate. So, India itself, where we are, right, its plate boundaries used to be defined as the Indo-Australian plate. Now, we think that a new plate is actually being created, something called the Capricorn plate, which is actually coming into being just south of India. There is a place where it's a part where there is a diffuse kind of ridge, maybe it will split in the future, but we have these different kinds of plates marked here. Notice, however, you also have these little boundaries here, right, which are marked. You can see they are called collision zones. So, these collision zones are also places where convergent movement between plates has taken place in the part or is still continuing. But these are the parts that actually give rise to mountain belts. These are similar to what you see in zones of subduction zones, but they are just at an advanced stage. So, now the whole idea is that the earth's surface itself is covered with major plates. So, in conclusion today, I mean, if we now take all this material together, the idea of plates has come into being. At the beginning of the 1960s, the debate was really around whether the earth's lid was rigid or mobile. A mobile lid model slowly began to be preferred because you had evidence from rock magnetism. You also, physics supported that the idea of a convecting mantle because the Rayleigh number was crossed. Then Tuzo Wilson's discovery of this chain of active volcanoes, right, which could be associated with mid-oceanic ridges or trenches and lines of extinct volcanoes, which Tuzo-Wilson discovered. These had ages which were progressively it should be ages progressively increasing, not decreasing. So, as you move away from the volcanic center, the age of the ridges would actually the age of the volcanoes would actually increase, right? And these could also be explained in terms of a mobile lid model. And it was also proposed that these rigid models were moving, rigid plates were moving over the seismic low velocity zone. Hotspots were between. So, this could actually explain the existence of these extinct mountain chains that you see. And finally, it was proposed that the entire surface of the earth was covered with these rigid plates, and all of these plates were moving with respect to each other. So, apart from this little typo here, right, I hope this point is now clear how this whole theory was coming into being. So, what we will do in the next class is to just take a look, right, at what would be the outcome, how the whole process would actually operate, and how oceans and continents would actually be formed. So, we will just take a quick look at that before we go into the details of plate tectonics. So, a whole set of references which really have historical value is actually documented. It was a very exciting time for the earth sciences when this whole theory was coming into being, right, and Tuzo-Wilson was the person who managed to get it all together. So, till next week then, we leave it at that. Thank you.